Hello and welcome to Science with Dr. J. This is episode number 7 and the title of today's episode is Monsters in Space. That's a strange title, and if you remember in the last episode we talked about the birth of stars. There are medium-sized or smaller stars similar to our sun, smaller than our sun, slightly larger than our sun. Today we're going to talk about stars that are much larger than our sun. How do they live? How do they die? Why do they die? And what happens when they die? When they die, they go with a bang, with a huge amount of violence. Tremendous explosions. The brightest and the most violent explosions known in the universe happen when these large stars die. And what happens after that is so bizarre and so incredible. And this is what we'll be talking about today, and how this works, why it works. So, again, in these big stars, the same thing happens. Hydrogen fuses into helium and tremendous amount of energy is formed. Then you have helium fusing into carbon, and then carbon and helium fuse together to form oxygen, and then again oxygen with helium in several steps, not one step. In several steps they fuse together to form silicon, and silicon is just, you know, the dirt, the rocks, the soil that we have outdoors. That's silicon. And that does not happen in one step. It happens in 2 or 3 stages. And as a result of that fusion, also you have a tremendous amount of energy. And then silicon fuses with helium, again in several steps, until finally it reaches iron. And when we have iron, things stop. No more fusion can happen. Why is that? Iron has 26 protons, and that's it. You no longer form any energy by fusing iron with helium anymore. Instead of generating energy, this fusion of helium and iron actually consumes energy. It needs energy. So when a star reaches this stage, that's it. There's no more fusion. It's not possible. So and that's because, as you can see in this graph, the lighter elements, lighter than iron, when they fuse, they generate energy. But as you reach iron, as you see here at the top on the left, the curve starts going down, meaning that in order to fuse, iron needs to consume energy. It needs to take energy from somewhere in order to fuse. It does not generate energy anymore. So what will happen to the star? If it stops at iron, then how do we get, you know, copper and nickel and molybdenum and silver and gold and platinum and uranium and all the heavier atoms? Where do they come from? If fusion is not possible when it reaches the stage of fusion where iron is formed, so what happens after that? How do we get all these heavier atoms? Well, we're going to discuss that very shortly. But this is when big stars start to die. You will find that iron, because it's heavy, sinks to the core, to the center of the star. And then you have layers upon layers of the lighter and lighter elements. So you have iron in the center, then you have silicon, and then you have oxygen, neon, carbon, helium, and hydrogen at the very top, because it's the lightest. So it becomes like an onion, you know, like a slice in an onion. So you have layers around the core of iron. Why does it die? Because if you remember, a star is a balance between gravity crushing things in and nuclear explosions ripping things apart, pushing them away. So when there's no more fusion, that means there are no more explosions. So what happens? The final explosions when Rn is forms such a tremendous amount of heat that the outer layers completely, because they're mostly in gas phase, they completely expand and they become huge in volume. If you remember from the previous episode, that's how we got the red giant stage in, for example, stars similar to our sun. But in this case, something more interesting happens, because gravity crushes everything into a very, very, very tight and small space. So the star shrinks to an extremely dense and extremely small core. Gravity wins. It always does. And the outer layers expand to become what we call a red supergiant, which means it's a huge, big red star, as I will show you shortly. Just to review a little bit, in the case of stars the size of our sun or smaller, when this happens, when the hydrogen is finished and there is more fusion, why don't they collapse like this? Why don't they collapse more than just a red dwarf? That's because there's something called the Pauli exclusion principle. The Pauli exclusion principle means that electrons don't like to be pushed close to each other. So if gravity tries to push them closer to each other, they resist because they like to repel each other. And as a result of that, we have what we call the electron degeneracy pressure. That means the electrons resist any pressure to crush them down any further. In order to be crushed down any further, you need a lot more mass than the mass of our sun, or a star similar to our sun, or smaller than our sun. It's just not enough mass to bring gravitational force to crush them any further. That's how strong the electron degeneracy pressure is. The electrons on the outside shell of the atoms completely resist any further pressure. But in the case of stars that are bigger than our sun, this is not the case. There is enough mass to actually crush these electrons. If you remember, the electrons are very far from the nucleus, from the protons and the neutrons. So to bring them, to close all that distance between them, and to force the electrons to crush down and join with the protons and the neutrons in the atom. In order for that to happen, you need to have a mass of 1.4 times the mass of our sun. 1.4 times the mass of our sun, or higher, then the electron degeneracy pressure is not strong anymore to stop the further crushing in, the star falling in on itself as a result of the force of gravity. This was actually calculated and proposed by an Indian young man. His name was Chandrasekhar, and in 1930 the Indian government decided to send him on a scholarship to study in England. His family objected. His mother was sick, his father said no, but he pleaded with them, and finally they agreed. And so in 1930 he went on a boat to travel to England to study in university. And during the long trip on the boat, he had pen and paper, and using pen and paper he actually came up with this calculation. And until now, this calculation is known as the Chandrasekhar limit, and it's 1.4 times the mass of our sun. This circle that you see here with a dot in the middle, that's a symbol for solar mass. And in fact, in every astronomy textbook until today, you find the Chandrasekhar limit taught there. This was such an important finding by this young man. He was only 19 years old, that in 1983 he was awarded the Nobel Prize. What an achievement. What a thrilling story. A very inspiring story. So, when the electron degeneracy pressure is no longer strong enough to resist the force of gravity, what happens? Electrons are joined with protons. When you join an electron with a proton, you make a neutron, because an electron is negatively charged. A proton is positively charged. When you join them together, you get a neutron, which is neutral charge. So can you imagine now the situation? You have a red supergiant, which is probably 1 billion kilometers in radius. There is a red supergiant like that. It's called the Betelgeuse, and the Betelgeuse is 640 light years away from us, which means this star is actually in the last stage of its life. It's ready to go supernova anytime. All right, so as a result of the crushing by the force of gravity of the core of the dying big star, the outer parts are completely blown away, and they are scattered and ejected and thrown into surrounding space, and that's what we call a supernova. And a supernova, it is so bright, it is so violent, it is so huge that when it happens, you can actually see that it outshines all of the other 100 billion stars in the galaxy, as you can see in this image here. But something very interesting happens. Something amazing happens as a result of that explosion. Like I said, the explosion is very violent, and it happens, within seconds, because the star collapses because of the force of gravity, and the outer parts are thrown out with a tremendous amount of heat, a huge amount of heat. That heat and that pressure is actually enough to fuse iron into higher atoms. And that's where we get all the higher atoms in the few seconds of the supernova explosion. During those few seconds of explosion, you form all of the higher atoms. Atoms that are heavier than iron are formed during that explosion. So you get copper and zinc and molybdenum and nickel and silver and platinum and gold, etc. So as you can see in this illustration here, all of the heavier atoms, heavier than iron, are formed during this powerful, tremendous, very bright and extremely violent supernova explosion. And the formation of these atoms, the formation of heavier atoms during this explosion, is known in physics and in astronomy as nucleosynthesis. That means the formation of new nuclei, new atoms, heavier atoms. And that's where they come from. So now, as you are listening to me right now, you're breathing oxygen. The oxygen that you're breathing was formed inside a big star like this. In your red blood cells, there is iron that connects with this oxygen that you're breathing so that it can take oxygen to all of your cells, so your cells can burn your food and make energy. That iron came from the guts of a dead star. Every single atom of everything around you came from the remains of a dead star, because this happens during a supernova explosion. There's another example of another supernova with all these elements formed and thrown out in space. So let's trace, how did all these heavier elements come to us? How did they reach us? Well, if you remember from the last episode, when our sun was born, and there was the first nuclear explosion that pushed all of the other gas and dust around it into orbits, there was the accretion disk was formed, and that accretion disk, these small rocks started getting bigger and bigger until they formed planet Earth. And that's exciting to know that everything that we have on planet Earth today actually comes from this dust, and this dust comes as a result of the explosion of huge stars. So thankfully we have such explosions in the universe, otherwise our solar system would not have had the chance to even form such a planet like where we live right now. And so truly, when you think about it, everything around you, everything you see came from these dead stars. And that's very inspiring. That's very exciting to know. Okay, so now let me explain to you about gravity. If you look at this image again of the Earth, you see there is any object that has mass actually curves space. Space and time are one fabric, as Einstein figured out about 100 years ago in his theory of relativity. Then you can see here that time and space are a fabric that can actually curve. It can be distorted, and it can be distorted by mass. So time can change and space can change as a result of mass. So mass curves space, and that is where we get gravity. So you can imagine now here Earth has curved space like this, and that's why the moon, as a result of this curvature or dip in the space, starts to go around the Earth in orbit because of that dip in the space caused by the mass of the Earth. Okay? So that's what gravity really is. It's not really a force that attracts, like magnetic force attracts things or repels them. Gravity is simply a consequence of the curvature or the dipping in space when you have any object that has mass. The heavier the object, the more the mass, the more there is dip, as you see in this slide here. Watch. On the right here, you can see Earth has curved or dipped space just a little bit. The Sun is 300,000 times heavier than Earth, and so it dips space a lot more than Earth does. When the Sun dies and becomes a white dwarf, the white dwarf is extremely dense, if you remember, very, very dense, but very small size, and that dips space even more than the Sun. And then in the case of a neutron star, when a star that is much bigger than our Sun dies and only the core is left, which is only about 15 or 20 kilometers in diameter, which is not very big, about the size of a city, when that happens, it dips space tremendously. So it creates a real deep curvature in the space around it. And then the largest curvature or disruption of space happens when a black hole is born, which we will discuss very shortly. So our focus today is going to be the last two, neutron stars and black holes. And how do they come to be, and what are their characteristics, and why are they important? So just to review again, electrons, because of the tremendous amount of gravitational crushing in of all the parts of the dead star, then the electrons are forced finally to join with the protons to form neutrons, and that forms what we call a neutron star. So a neutron star is an extremely dense core of a dead star, a very large dead star that died, and what is left of it is what we call a neutron star. So the neutron star could be 15, 10, 20 kilometers in size, so it's extremely dense. Can you imagine that a huge part of the mass of the dead star was condensed and crushed in to this very, very, very small size, the size of a city? So that can be extremely, extremely heavy. How heavy? Well, some astronomers calculate for certain neutron stars, if you take only one spoonful, just one spoonful, it can be as heavy as 400 million tons. From other stars, more dense, other neutron stars, more dense, can be as much as 1 billion tons. One spoonful, 1 billion tons. You know what happens if you put one spoonful of 1 billion tons of planet Earth? It'll go right through it. That's how dense it is. So, what are the properties of neutron stars? Well, first of all, as I just mentioned, they have tremendously, incredibly strong gravity. Why is that? Because they're very, very high density and very, very small size. And that creates a tremendous dip or curvature in space. And the amount of gravity, the gravitational force that you will feel around the neutron star is unbelievable. It is mind-boggling. And if you remember from the conservation of angular momentum that we discussed in the previous episode, when someone is ice skating and they go with their arms like this, if you remember, the center of their mass is not very far from most of their mass, because they're putting their arms close to the center of their body. So they start spinning faster. And when they go like this, they start spinning slower, because the center of their mass is far away from a lot of their mass when they spread their arms like that. And so in a neutron star, as you can imagine, because you condense all that tremendous amount of mass in such a small volume, then it starts spinning and spinning and spinning extremely fast. And as a result of that spin, they create a very powerful magnetic field. So these are the characteristics of a neutron star. They have strong gravity, they're very dense, they're very small in size, they spin very fast, and they have a very strong magnetic field. Okay? In fact, the magnetic field is so strong that if you take a credit card, which has a magnetized strip on the back, that it can actually erase the information on your credit card from a distance of 100,000 kilometers. That's a very powerful magnetic field. These neutron stars, some of them, as they spin, they eject a tremendous amount of radiation from both poles, and that radiation can be measured or sensed, and so when it does that, then we call it a pulsar. So a pulsar is a neutron star that produces a huge amount of radiation from the poles, and if it is pointing towards Earth as it's rotating and pulsing, then we can measure that radiation. And it can happen, sometimes these pulses can happen maybe 5 or 10 times a second, and sometimes for some of these neutron stars it can be as high as 700, 800 times per second. 800 pulses, that means it's rotating 800 times per second. Can you imagine the power of such a star? It's really, really bizarre, and it's amazing that nature, with simple laws of physics, has created such monsters in space. And some neutron stars, in fact, the magnetic power that they generate is absolutely tremendous, and it is so huge and so big that it causes star quakes. And on Earth we have earthquakes. On these stars we have star quakes, and they release a tremendous amount of X-ray. So if they have such a tremendous amount of magnetic power, then these stars are known as magnetars. So a magnetar is a neutron star that has really, really a huge and extremely powerful magnetic field that's 1 billion times stronger than a magnetic field on Earth. Now we talk about black holes. What's a black hole? Well, why would anything be black? Anything is black is because when visible light hits that object, if it absorbs all that light and doesn't let anything go back or get reflected back, if it's completely consumed by that object, then it's black. You can't see it. If you remember, in the neutron star, neutrons are formed, and so they stop gravity from going any further. Then in a black hole, the mass of the star in a black hole is so big and so huge that it actually crushes the star to almost a single invisible point. which is called singularity. So it's gravity gone mad. That's what a black hole is. Gravity that has gone to the extreme. And in fact, gravity in the black hole is so powerful that even light cannot escape it, as I will show you shortly. Watch this. To explain exactly how that works, I'm going to show you an illustration here. Imagine someone holding a ball and throwing it up in the air. The ball will go up, as you see here, but then because of the gravity of Earth, it starts to slow down, and then it stops, and it starts going down again. So now imagine this person throwing the ball with more force, so it will go higher. It will go higher, but still, because of Earth's gravity, it will stop, it will slow down, and then it will stop, and then it starts falling back to Earth again because of the Earth's gravity. Now what happens if he can actually throw that ball up in the air with such tremendous force that it will not come back to Earth? Well, how much speed does that ball have to have in order to go up in space and never come back? 11 kilometers per second. If you throw an object with enough force to give it a speed of 11 kilometers a second, okay, which is 40,000 kilometers an hour, 11 kilometers a second translates into 40,000 kilometers an hour, because you multiply 11 times 60 times 60, you get about 40,000. Then that ball will go up in space and never come back. It will escape Earth's gravity. This is called the escape velocity. The escape velocity on Earth is 11 kilometers per second, or 40,000 kilometers an hour. Anything that leaves Earth at this speed will go out away from the gravitational pull of Earth, and it will go in orbit around the planet Earth. As you see here in this rocket, that's why you need a tremendous amount of jet fuel in order to enable to burn it and to create such a huge force to push it upwards so that it can escape from the Earth's gravity at the speed of 40,000 kilometers an hour. That's what you need, and that's why you need a huge amount of fuel to take a rocket from Earth into orbit up in space. Otherwise you can't do it, because you need that kind of force in order to gain that kind of velocity so that it escapes Earth's gravity and goes in orbit around the planet. So now, if you remember, the speed of light is 300,000 kilometers per second. That's a lot more than 11 kilometers per second, which is the escape velocity needed to escape from Earth. The speed that you need in order to escape from a black hole should be more than 300,000 kilometers per second. But we know that nothing can go faster than the speed of light. Therefore, nothing, not even light, can escape from the gravitational pull of a black hole. So even when light hits that black hole, it is completely taken by the black hole, engulfed by the black hole, and it cannot escape. And that's why it's black. That's why we can't see it, because there's no light coming back from it. Okay? So even light cannot escape from a black hole. Well, let's just do a thought experiment here. Let's just imagine planet Earth, which is about 12,700 kilometers in diameter. How much do we have to crush planet Earth into a small size so that it becomes a black hole? You'd have to shrink planet Earth down to the size of 9 millimeter radius, which is about 1.8 centimeters diameter. Okay? So if you crush Earth with all the mass in it, Earth becomes a black hole. Of course, there is no force possible. The Earth will never become a black hole because it's not possible for it to be crushed down to that size. So this is just a thought experiment. So now, normally on Earth, if you take an apple, it's about 100 grams. If you hold an apple in your hand, gravity is pulling it down. The force of gravitational pull of the apple is about 1 Newton. All right. So now, if Earth is shrunk down to 1.8 centimeters diameter, instead of 12,700 kilometer diameter as it is right now, then what happens? Well, the force changes now from 1 Newton to 1 billion newtons. That's a gravitational pull that Earth will exert on the apple. That's the force that the Earth will exert on the apple, the same apple, if Earth is shrunk down to 1.8 centimeters. That's incredible. It's unbelievable. Just to help us comprehend, a billion newtons. Instead of 1 Newton, a billion newtons. How big is that? Well, one of the tallest buildings in the world is the CN Tower in Toronto. The CN Tower in Toronto, Canada, is 553 meters high. And it's massive in weight. It's huge weight. Okay? And just to help you understand how much a billion newtons are, imagine you have 7 billion of these CN towers crushing down on planet Earth of 1.8 centimeter diameter. That becomes the weight of an apple if Earth is shrunk into a black hole. So black holes are very powerful, extremely strong gravitational pull that is simply beyond imagination. They completely curve and disrupt the space-time below them so that it becomes completely distorted and curved to the maximum. So as you can see in this illustration, a black hole is therefore an object where gravity has gone mad and crushed everything to such an incredibly small size that in order to escape from it, you have to go faster than the speed of light. And since nothing can go faster than the speed of light, then it becomes a black hole. As you can see here, even light cannot escape. At the very edge, we call it the event horizon. The event horizon is the point that inside it, you need to be going faster than the speed of light, which is not possible. Therefore, once you are inside a black hole, you cannot get out. It's a point of no return. But outside it, slightly less than the speed of light. Farther away, slightly less than the speed of light you have to go, and then you are safe. The black hole will not engulf you if you are at a safe distance away, because you can go slower than the speed of light when you're farther away from a black hole. But once you reach the event horizon and you reach that point, then you need to go faster than the speed of light, which is not possible. And that's why everything that comes close to the event horizon of a black hole is sucked in, eaten, consumed, destroyed instantaneously, and it will never go back. To give you just an example so that it will help you understand, imagine someone on a kayak going on a river. It's a nice quiet river, it's not very strong. But if the river starts to get stronger, that person that's on the kayak has to paddle a bit harder, otherwise he'll be carried away by the strong current of the river. But there comes a point, if he's not careful, there comes a point when he reaches the very edge of a waterfall. And at that point, if he reaches that point, the event horizon, so to speak, he cannot go back. No matter how hard he tries, he's not going to be able to run away from that, and he will fall into the waterfall. Okay? And that's a similar situation in a black hole. When you are not able to resist or go faster than the speed of light, which is impossible, you're sucked in the black hole. And so in a black hole, there is also an event horizon where it is just the edge of safety. If you are there, you're sucked in. If you are before that and traveling at high speed, you will not be affected by the black hole. So let's imagine what happens. What happens if this person here is coming towards a black hole? When she reaches the event horizon, at that point, That's it. There is no return. She cannot go back. She'll be sucked in. But because the black hole is extremely dense and extremely powerful gravitational pull, the gravitation on her feet, the gravitational pull on her feet, will be so much stronger than the gravitational pull on the top of her head. So much so that she is stretched. She is stretched like spaghetti. And in fact, that's what astronomers call this phenomenon. They call it spaghettification, that you are stretched like spaghetti, like this. The radius from the center, the singularity, where the mass of the black hole is, to the event horizon, is called the Schwardzchild Radius. Is the distance between the center of the black hole, where there's a singularity, and the event horizon. So, in something interesting about black holes, that smaller black holes, believe it or not, are more hot than larger black holes or more massive black holes. So there's an inverse relationship between the mass and the temperature of a black hole. If it has smaller mass, it has higher temperature. And if it has larger mass, it has lower temperature. A very famous physicist, astronomer by the name of Stephen Hawking from Cambridge in England, he calculated that black holes over trillions of years will actually evaporate. They lose mass. And this is called the Hawking radiation. Of course, this is a simplified description. There are tremendously complex physical and mathematical calculations that you have to go through to understand this. It's beyond the scope of these episodes, but I just want you to be aware of the scientist, Stephen Hawking, and of the description of how black holes can, over trillions of years, actually completely disappear and evaporate. So a black hole is so powerful that it can eat and devour and consume an entire star. As you can see here in this illustration, this star is being completely consumed by the black hole. And as you can see, it is being stretched, okay? And then eventually completely sucked in and destroyed. But it is stretched because the gravitational pull on the closer part is much, much stronger than the gravitational pull on the farther away side. But eventually the whole thing is sucked into the black hole, and that's the end of the star. It joins the black hole, and the black hole gets bigger, and then starts eating more and more gas and dust and stars and whatever comes close to the event horizon. Now, something interesting about black holes is this, that in the center of every galaxy that astronomers have observed so far, there's a supermassive black hole. What is a supermassive black hole? It's a black hole that can be probably 1 billion times more massive than our sun. It's unbelievable. These are monsters. 1 billion times heavier than our sun, and a black hole in the center of every galaxy. So a lot of astronomers believe that black holes actually play a very important role in the formation of these galaxies. And if you go into astronomy or physics later on in your career, then you'll be able to study these things in detail. I just want you to be aware of the terminology and the description of black holes. Some black holes emit such a tremendous amount of radiation. These black holes can be, they can emit a tremendous amount of radiation. Can you imagine? More bright than all of the stars in the galaxy. So some of these black holes can emit that kind of radiation and that kind of brightness. So they are really, really monsters. They're very powerful. So the radiation that leaves the black hole from the top and from the bottom, from the two poles, is called gamma ray burst. If you remember, gamma rays are very, very, very short wavelength and extremely packed with powerful energy. Okay, very high energy, very short wavelength, and these are the gamma rays. And if you remember that from previous episodes, these gamma rays can be lethal, because these gamma ray bursts, if they ever hit planet Earth, they will completely evaporate our atmosphere and boil all the water of the oceans into vapor, and in fact the temperature of the planet will be in the thousands of degrees and will be completely roasted and destroyed. So gamma ray bursts can be a real danger. Fortunately, we don't know of any gamma ray bursts that are close enough, and in black holes that are close enough to planet Earth to cause us any harms. And so we are very fortunate to be tucked in the middle between two arms of our galaxy, the Milky Way, where there aren't that many stars, and we're away from all that dangerous action, because if we were closer to them, then we could be subjected to this, and it could be a complete destruction of planet Earth. So NASA incidentally has two satellites out in space to study gamma ray bursts and supernova remnants. So one of them is called the NuStar. The NuStar satellite is, the purpose of that is to study gamma ray bursts, and also another one is called the SWIFT satellite. The SWIFT satellite is also has a mission to study gamma ray bursts, an abbreviated GRBs. So I just wanted you to be familiar with these missions, so that you are aware of what's happening in the world of astronomy. So now we come to the end of episode number 7 about monsters in space. I hope you enjoyed it. Please join me again next time on the next episode, where I will discuss more in depth about other things in space, gravitational lensing, and about gravitational waves, and about the fate of our universe. How will it end? So these are the subjects that I will discuss in our next episode. Thank you for joining me today. I hope you join me again next time, and please subscribe to the channel if you can, and inform your friends, share with your friends, let them know about this, so we can all enjoy this amazing journey into our wonderful universe. Bye for now.